Hello, my name is Eungbeom Yeon. I will start my first talk now. I first want to express my gratitude to Hoju Lee to offer a great chance like this. Here is a table of contents that I will follow. First, I will briefly introduce capillary minimal surfaces and historical results of their characterizations. Second, I will cover some of the preliminaries that was used in the proof. Most of them are elementary ones, including the Weierstrass representation theorem. Lastly, I will talk about my results on characterization of capillary minimal surfaces outside the unit ball. So I will start with this capillary minimal surfaces. A capillary minimal surface, sigma in a domain U, is a minimal surface, sigma, which meets boundary of U in a constant contact angle along boundary of U. When the contact angle is a right angle, the surface is called a free boundary minimal surface. The most frequently studied examples of capillary minimal surfaces are obviously planes and the critical catenoid. So this is the simplest example, and then we have the critical catenoid. Meaning this unit sphere orthogonally. Throughout the years, we have some of the interesting results on characterizations of them, but only a handful of results are concerned with their characters as capillary surfaces. For example, there is a famous result by Nietzsche. So Nietzsche proved that the only free boundary minimal disk in B3 is an equatorial disk. And Ross and Swan in 1994 generalized Nietzsche's result to space forms as S3 and H3. And Fraser and Shane in 2014 generalized this Nietzsche's result again to higher dimensional Bohr, but theorem only holds for the surface case as well. So in fact, fundamentally, these three theorems all use the idea from the Nietzsche's paper that it can be put like this. So free boundary condition controls the second fundamental form of the surface. We will talk about this later on. So another result by McGrath in 2018, he proved that embedded free boundary minimal annulus in B3 symmetric to three coordinate planes must be critical catenoid. And this is the partial result to the Fraser-Lee conjecture. Fraser-Lee conjecture states that asks that if the only embedded free boundary minimal annulus in B3 would be the critical catenoid, and it is remain unsolved for now. Interestingly, there is another method to prove Nietzsche's result using half-index method, and Choi in 2002 generalized Nietzsche's result to domains bounded by several spheres. Now we review some of the elementary methods, including the Weierstrass representation formula. So the pair G and DH is called the Weierstrass data, and it consists of a Gauss map GZ of the surface and a holomorphic differential DH, where x3 is the third coordinate function defined on the surface. So this immersion x can be represented by the real part of the holomorphic curve as follows. Conversely, if a meromorphic function g and the holomorphic differential dh are given like this, then we get an conformal minimal immersion. If the metric is well defined and there is no real period, so there are some restrictions that the metric should be well defined, and then there should be no real period. With the Weierstrass data, various geometric invariants can be also represented by the data. So there are first and second fundamental forms. It can be represented by the data as follows. Here, V is the tangent vector to the surface sigma. And then also the Gaussian curvature K can also be represented by this data as follows. So exploiting the Weierstrass data, minimal surface theory flourishes in R3. Here are some of the examples. So the simplest example would be the N-Ampere surface. It is defined on the simply connected domain, and GZ and DH are given as follows. And there is a catenoid also, and it is defined as follows. And we can deform N-Ampere surfaces and in various ways. First, we can also consider higher dimensional N-Ampere surface, and it's also defined in this simply connected domain, and Gauss map becomes z to the k, contrast to the original N-Ampere surface. So it has higher multiplicity at the end. And we can deform this end of the surface to get some other surfaces, uncountably many surfaces like this. So here is an example. We could set GZ to be a still holomorphic function, and then DH to be GZ DZ. Then it gives us an well-defined minimal surface, and here PZ should have degree less than or equal to n-1. There is a more complicated example. So here is an example. So it is called half N-Ampere and half catenoid example. So it has two ends, and one end is asymptotic to the N-Ampere's end, and the other end is asymptotic to the catenoidal end. This one here is very interesting example because as any per surface here has vanishing flux vector. But as we see in this example, even though this end, one end is totally asymptotic to the NA per surface's end, but this surface has non-vanishing flux vector on the first homology class of the surface. So NA per type ends can both have vanishing or non-vanishing flux vector on the first homology class of the surface. So there also is a field of line elements that I used in the proof of the theorem. So a smooth field of line elements is a vector field defined on a region that is a family of curves such that at each point of the vector field is tangent to a curve through that point. A field of line elements cannot be extended to a single point P. Then it is called a singularity of the field of line elements. And the index of an isolated singularity P of the field of line elements is defined as J, where 2 pi J is a rotational number around a singular point P. So here are examples of singularities. So this one and this one and this one are, we can easily see that these are singularities in line of field elements, and it has the singularity, it has the index of 1 and 5/2 and minus 1/2. And we have the following theorem. It is called the Poincary theorem, and it states that if F is a field of line elements on a closed surface S of genus G with finite number of singularities pi, then sum of the index of along the singularities is just equal to the Euler characteristic of the surface. Now I will introduce some results on characterization of capillary minimal surface outside the unit ball. To consider capillary minimal surfaces outside the unit ball, we briefly talk about embedded ends of minimal surfaces. So we are considering a surface like this. There is a unit ball, and the surface stays outside this unit ball here. So if we impose restrictions for the surface to have finite total curvature, and one embedded end. This embedded end can be explained by the Weierstrass data also. In fact, this is another good example where the Weierstrass method shows its strength. in 1983, Shane showed that this embedded end only has two types of ends. One is catenoidal end, and the other one is the planar one. So we want to show that if this surface outside the unipole being free boundary, uh, it is unique or not. Now we have the following uniqueness theorem. It states that if X is a capillary minimal surface in outside the unipole with finite total curvature and one embedded end, then it must be either part of the plane or part of the catenoid. So here's theorem 2. We was also able to obtain the following non-existent theorem as well. So it states that there does not exist a capillary minimal immersion with also finite total curvature and one end asymptotic to the end of the unappeared surface, and also vanishing flux factor on the first homology class of the surface. So it basically states that if flux factor on the first homology class of the surface vanishes, then there is no such surface outside the unipole asymptotic outside the unipole whose end is asymptotic to the end of the unappeared surface. And here's theorem 3. Motivated by choice work mentioned earlier, we were able to show the following theorem. So let U be a convex domain which is bounded by several spheres. So not just one sphere, but it is bounded by several spheres like this. And also we are considering a capillary minimal surface in R3, this outside this domain, with finite total curvature and one embedded end. So if K is bigger than 1, then the surface with a catenoidal end cannot exist. Furthermore, the surface with a planar end must be part of the plane. Since theorem 3 is not very different from the previous literature, we now look into main ideas of proof of first two theorems. So there are two important lemmas. First lemma tells us that how free boundary condition controls the second fundamental form. Namely, if we put phi z dz squared here to be a Hopf differential defined on the surface, and put z squared phi z to be a holomorphic function here. Since phi z is holomorphic, it is well known that on minimal surface phi z is holomorphic. So alpha and beta are harmonic functions. In case where the surface has planar end, we can find that alpha and beta satisfies the fact that it vanishes on the surface. In case the surface has a catenoidal end, alpha must be some non-zero constant A and beta should vanish. So we can express phi z as follows. Where L and N and M are coefficients in second fundamental form, then the result, these results are telling us that we can express z squared phi z to be some constant c. So in this manner, we can see that free boundary condition controls the second fundamental form. So now Lemma 2 explains what it means for phi z to be c over z squared. So we found out that phi z is c for some constant c over z squared. So Lemma 2 directly tells us that what this means. So let a minimal surface d prime to sigma be as in the theorem 1, and assume that it has the catenoidal end. Then all concentric circles centered at the origin of d prime become lines of curvature of the surface, and there is no umbilic point on the surface. So we can visually present the Lemma 2 as follows. Since the surface has finite total curvature, we can parameterize the surface in a punctured disk d prime, so that we have the immersion x with the surface outside the unipole. So uniformization theorem tells us that since we have that we are assuming that the surface has finite total curvature, we can parameterize the surface with conformal coordinate z in a punctured disk, so that the Lemma 2 is telling us that the concentric circles here are all the lines of curvatures. So it goes like this. So we immediately find out that the surface is foliated by lines of curvature, and then it has no umbilic point. So since there are a lot of calculations, we just look into the main idea of the proof of the theorem 1 here. In a planar end case, Lemma 1 basically tells us that the surface is totally umbilic, so we are done. So we only consider the catenoidal end case. And we consider the following situation. Main idea is that we reparameterize the surface with the Gauss inverse of the Gauss map. Inverse of the Gauss map only exists in a local manner since G prime is not 0 by Lemma 2. So here is the Gauss map, and here is the inverse of the Gauss map. So we don't know that the image of d epsilon under the Gauss map is a concentric disk, but we still know that we can reparameterize the surface with the inverse of the Gauss map locally. So if we accept this fact, then we can put the Weierstrass data in W coordinate as follows. So as you see, we have very simple expression with the new coordinate W, and we have to be very careful because since tangent vector to the line of curvature like this goes to this vector here, and it's no longer orthogonal to the position vector. So it's always orthogonal to the position vector here, but it's not like that here. So we have to be very careful. So after some calculation, we can find out that the image of the partial d epsilon, so this is partial d epsilon, the boundary, under the Gauss map must be a circle. Indeed, the domain G d epsilon here, so this is the domain G d epsilon, must have lines of curvature emanating from the puncture, which also has a property that the tangent vector points the radial direction at some point on the line of curvature. So it means that there is a line of curvature emanating from the puncture here, and it still has the property that it must be tangent. It must be tangent, that tangent vector that is parallel to the radial vector. So then it can satisfy those properties only when this line of curvature is just a straight line. So after some calculations, we can find 4 such lines, which is only possible when G d epsilon is just a round disk. So with this new parameterizing technique, we can actually prove that the uniqueness of the theorem. So we now look into the proof of theorem 2. In case where the surface has end asymptotic to the end of any surface, we do not have lemma 2 here. So we have to be careful that we don't have the lemma 2. It means that we can now have a possibility for the surface having a boundary umbilic point. So we now so the above picture, we are considering the boundary umbilic point here. So this P is boundary umbilic point. So we are now trying to show that there's no boundary umbilic point using the index theory. So after some calculation, the only possibility with this boundary oblique point is that it has the index -1/4. So we are assuming that this singularity has index equal to -1/4 here. So it has to be then the lines of curvature must look like this near P, and then we can find out that there are 3 parts on the domain. So one part is part A, and the other part is part B, and the other one is part C. Then we can find out that on part A and part C there must be an oblique point with positive index, because lines of curvature, the shape of the lines of curvature tells us that. So it means that phi z has a pole other than the puncture. So this is an immediate contradiction. So we find out that there is no boundary oblique point. So after finding out that there is no boundary oblique point, we can proceed as follows. So we have the fact from now that z squared times phi z, as before, is alpha plus I beta. And then we know that for a fact that the geodesic curvature along the boundary of the surface is computed as the alpha over lambda, where lambda is the metric vector. Then we now know that there's no boundary oblique point. It means that alpha never changes sign along the boundary. So it means that it must be positive or negative along the boundary. So we, without loss of generality, we just assume that this is positive. Then we see that the boundary of the surface only turns left with respect to the tangent great circle along the boundary. Just geodesic curvature geometrically means that if it is positive, then it's locally convex. So it has to turn left with respect to the tangent great circle. It means that the boundary must be contained in a certain hemisphere. So now recall that we are assuming that the surface has a vanishing flux vector, but it contradicts the assumption, because along the boundary, the flux vector has a non-zero component to the vector parallel to the north pole of the hemisphere. So it's just a direct contradiction now. So it means that we are done here, and there is no such surface with vanishing flux vector and with one end asymptotic to the anapure surface's end, and such surface cannot exist. So I will finish the proof of the theorem 2 here, and then I will wrap up my first talk here as well. So thank you for listening to this talk, and I really want to thank again to Ho Lee for all the work he has done to hold this event, and thank you again.